Hello, ladies and gentlemen. Welcome to episode 3 of Roundtable Ruckus. My name is Danny, coming to you live from the AndyMark studios. With me this week is Ruth, our social media marketing specialist. Maybe not. And on this week's episode, we are going to talk about game piece collection and considering weight as part of your robot design. With the new weight allowance this year within First Tech Challenge, weight's a big issue that people are going to have to deal with. So Ruth, I botched your title. What do you do here at AndyMark?
You actually got a lot of what I do correctly, Danny.
You're being kind.
I've been accused of that once or twice. I'm a marketing specialist here at AndyMark, so if you see a social media post or anything like that, I'm usually the person behind it. And I also write a lot of the newsletters, take into consideration how we're going to share new products with you guys, as well as generally produce the content behind the scenes for these shows. So it's neat to be in front of the camera this time.
So you might say that some of this was your idea.
Sorry about that, Danny.
Okay, so one of the first things that we like to get into with each one of these shows is kind of trying to understand some of the game challenge and kind of understand what we're trying to overcome. And so in order to kind of break that down, we are going to transition over with one of the coolest fade outs imaginable to our whiteboard. So we're going to go ahead and get that out. All right, so we have a couple high water marks that we're going to kind of be talking about today. And the first one, got to save that for later. The first one is the game pieces. We have a 2-inch cube generally placed on the field, waffle side up, and a 2.75, 2.8-inch ball. Now, one of the cool things about these balls, different from standard wiffle balls that you might see in gym class or wherever else, they're really, really hard, really rigid. It is the same ball that we've used in First Tech Challenge, going back to Rescue and Cascade Effect. So there's probably quite a few teams out there that have some experience with this ball. But one of the interesting things that we have this year is a really small carry limit, really low limit on what robots can carry.
You can only carry 2 total, right, Danny?
2 game pieces, 1, 2. 1 game piece is all you're allowed to carry. And so you can carry 1 ball, 1 cube, 1 silver, 1 gold, 2 of each, but 2 total max across the entire robot. And so that kind of limits us in some of the things that we can do from a design standpoint, but also gives us some opportunities. We don't need huge hoppers. We don't need huge, super efficient, time-saving collection devices.
It's also a challenge that teams should be used to from last year's game, Relic Recovery, where you could only have 2 of those cubes. But we're dealing with definitely a size change, Danny, and also how squishy the game objects are, right?
Absolutely. Now we're going to start doing this. First is a game that's played in color, so we're going to start doodling in color. I think that most everything is probably best, usually starts with a good map of the field. And so
we're playing zones opposite this year.
I'm drawing for the camera.
Right, but they're opposite sides of the field this year.
That's very clear. It's really important for all of you out there, roboteers, roboticists, and whatnot, to really read the game manual and really understand what's going on and understand all of the intricacies that go along with the game manual. There's a lot of questions that can be answered just by simply reading the game manual. And so we've got some design challenges that are kind of go along with that. Now, we have our dome down the middle, and we have the silver goals face the craters. So we know that the field is actually like this. So this is for cubes, and this is for balls. And then, oh, you have the red Sharpie. Balls and cubes. Sweet! I'll probably hold all of these throughout the course of the day. All right, so now we know that game pieces start in the craters. There's a couple that start around here. Quantity-wise, those are going to be a little insufficient to really kind of care about. If you can pick up from inside the crater, you can probably pick up from the open field zones as well. So now some of the things that, one of the first things that's probably important to kind of design and consider, and this is a challenge that goes for FTC, FRC, like this is something that robots and teams have been facing for a very long time, and that is the issue of the 180-degree turn.
That is a big issue, Danny.
Do you have one or not?
Right, so you can opt for simplicity in your collection mechanism by only having one in, one out, but then you got to turn your entire robot. Or you can build a more complex mechanism that builds in your collector to your depositor that goes all the way through your robot. So you don't have to turn while you're driving, but you do have to have that added complexity and weight of those combined systems.
Exactly. Now, one of the other things that we're going to have to look at in terms of system integration, and this maybe is something that we've touched a little bit on this in previous videos. I think we'll come back to it again in post videos. Is sort of how your mechanism, your intake, loops around with the entire system of the robot. And one of the other considerations is, do we go into the crater with the chassis of the robot as a whole, or do we just reach in with the grabber? Now, one big limitation is the crater's pretty big. And so to develop a reach long enough to get game pieces late in matches that may be hanging out in this back corner, we may have to end up getting the robot down inside of the crater. So we should probably be pretty good at doing that. So tackling the crater from a drivetrain standpoint, it's probably going to be something worth putting our time and effort into.
And if you missed last week's episode on drivetrains, you can catch that on our YouTube channel.
Great plug. So we, if you roll the video back, you can see my train of thought just utterly leave to the left of frame. So we're talking about the 180-degree turn. Now, there's a lot of mechanisms that that maybe don't require that 180-degree turn. And so, if this is my robot, we've got our wheels here, we've got the sweet crater-looking thing doing like this. We reach over and we grab some game pieces over here, and we know the lander, nice and big, is over this way. There is kind of what looks like a pretty straightforward path.
That does look pretty straightforward, Danny.
Pretty straight. And so now that on a real field, it's pretty long. It's like 4 to 6 feet, depending on how far into the crater that you're actually looking at. But we may find a deployable conveyor belt system, that we could move through this way, or depending on where we say maybe pivot an arm to reach in this way and to reach up. Maybe we don't have to park the robot. Maybe the robot just does a little shuttle drill back and forth, and now we're only moving, say, 2 feet. But now that means our robot's a lot simpler because we don't have a 6-foot-long setup, but only a small arm and a short drive. We've got a drive base, might as well use it.
Exactly. And I mean, if you're going to do that sort of driving, you may as well optimize your drive base for not turning. As weird as that sounds.
Yeah. Yeah, that does sound odd. But, if a lot of the things in this game, we're going to have, some small little, turning maneuvers. We're going to have some little lineups. Depending on how we grab game pieces, we may or may not. We may be able to do that more with the end effector than the drive base of the robot. So, the little fine lineup maneuvers, maybe we do have these really wide open goals here. So being able to line up really accurately left-right, probably not that important. So then I guess we'll just sort of diagram here the other style of robot. We've got our lander sort of like this and our crater sort of like that. Now a robot that might need a 180-degree turn every time it drives back and forth, we're going to have the collector off the front. We're going to score off the front as well. So we're going to need to execute that spin within the drive base. Something like if we're not going into the crater, something like a Mecanum chassis. Mecanum chassis actually spin faster than anything else because they have all their forces are perfectly aligned in the right direction for that. but a 6-wheel drive, drop center drive base like the Tile Runner, like West Coast Drive, those also are really good in a spin. And the more drop that you have in the middle of the robot, the easier it is going to be for those spins. So this is one of the things where lots of different facets of the robot are all sort of interdependent and intertwined within one another. So that mechanism looks quite a bit simpler, but maybe takes a little bit more to execute. But this robot may be a little bit more optimized at going for the cubes, because it needs to drive, it's going to collect here, it's going to do a little 90-degree spin, loop its way around here, and come after the cube side goal, the gold cargo hold. And so this robot, you can take out some of that spin in place by going for the other goals, whereas a robot with a pass-through mechanism, some might say a car wash style mechanism, those would be more optimized for going after the silver, because they can just run that little shuttle back and forth.
I think it's safe to say that if you went with the 180 design, you're really going to have to optimize for speed and maneuverability in that, both in your collector and your drivetrain. So you're going to need to consider cycle time, how long it's going to take you with that mechanism to get there, and how familiar and how quickly your drivers can work on that process, or whether maybe you want to automate some parts of that.
Ooh. Having a button that does a coordinated 180-degree turn might be something that just saves you a lot of time, and especially if you have some sensors, some encoders on your drive base, you may be able to program that in so it does an exact 180-degree turn every time. I am a big fan, though, of I come from a mechanical side. I think that the best sensor out there has always been a pair of Mark I eyeballs. I don't know. I don't know that there's much to beat those.
I don't know. I'm kind of with you on that, Danny. The human reactions can sometimes be a lot faster than pre-programmed sensors.
It's true. So some of the things, so this is sort of robot archetype. I have a sweet field here, so I think we should leave that. But there's two more. No, we need a clean sheet. There's two big styles of intakes or grippers that we see sort of throughout the first world. Even from Lego League, First Deck Challenge, and FRC. One being the claw gripper. Simple, easy to explain. Two elements come together like Cymbal Monkey. And you can do this a lot of different ways. You can put, you can have one side be fixed and one side move. You can have both move together. You can have independent control over both sides. There's a lot of different ways that you can optimize these, but ultimately in the end, a claw that goes and grabs, one of the other things to keep in mind is, do you grab left to right or top to bottom? So claws sometimes get optimized further into an open-sided box with a trapdoor. We've seen some of those. I remember a sort of famous one from Block Party. There you could only hold 4 of these cubes, and so a robot had sort of a 90-degree wedge, a floor plate, and then they'd apply a little bit of pressure down from the top to sort of hold everything in place.
Kind of like a dustpan.
Yeah, very similar to a dustpan. And so there's a lot of ways that you can do that really simply, and with the small number of game pieces, remember just 2, I think a lot of teams are going to look to a claw as something that could be really effective for this year. Now, one of the challenges that we have, and one of the places where a claw is going to need to be a little adaptable, is if we want to try to hold a ball and a cube at the same time. If we want to try to hold, and a claw that, like the first one here, a claw that can swing through and grab 2 cubes or 2 balls, probably a pretty straightforward thing. But a claw that can grab 1 of each maybe is a little bit harder. Although, that could be a benefit, because as we know from our field map, the balls and cubes have to be scored in separate places. And so by having a claw that is optimized around grabbing 2 balls or 2 cubes means that every time I go to deposit, I'm going to either one goal or the other, and I'm not trying to deliver a ball here, circle around, a cube there, and waste time sort of on that back and forth.
Yeah. So, Danny, what happens if you do get the opposite game piece in the wrong scoring container?
Can I have the fans at home leave a comment in the description below?
That would be really good.
We should do that. So, yeah. What happens when you put the wrong mineral in the wrong cargo hold?
Something to consider. And people who are curious about that and how do you solve that problem may want to tune in next week when we talk about sorting.
That is your second shameless plug of the night. I think one more and we might be out.
Hashtag AndyMarketing.
Oh! You picked up where Bilford left off, didn't you?
Sorry, not sorry.
Hi, Bilford. The second major type, and it was really sort of an iterative step off of the claw, and so its name is just simply claw with an adjective. That'd be the roller claw.
Ooh, that's a popular one. We saw a lot of that last year in both First Tech Challenge and First Robotics Competition.
Yes. Indeed, indeed. So where these are top views, we'll draw maybe one from a side view. And like the regular claw, there's a lot of different ways to orient these. So a horizontal axis, wheel spinning this way to pull game pieces in.
So something a bit like this.
Yes. We even have wheels there we could demonstrate.
Ooh.
Bingo. Or, for something grabbing, we saw this with, exactly. We saw this with the cubes last year, but, something where you'd have a vertical axis roller, or maybe a pair of vertical axis rollers around a framework.
So maybe something like a stack of wheels.
Exactly. Now these are going to spin together and pull game pieces in. Either one of these can work nicely. One of the things that we have to kind of keep in mind with a system like this is this little lip, how it interacts with the front leading edge, whether the lip hits first, whether the wheel hits first, how this lip is going to interact with the variable terrain of the soft tiles. Mm-hmm. So just some things that can largely be solved just by prototyping and iterating and trying things out. If you make this with a big hunk of material, it doesn't work. You cut it off a little bit. You trim it back until it works. Trim it back until it works. You're not wasting material. It's just part of the evolutionary development process.
That makes a lot of sense, Danny.
Thank you.
Were you doing some prototyping earlier today?
I don't know that we're ready for that segue yet. Can we have Dean writing a segue? Ooh.
No.
Dang it. There was one more that I had on my list of thingies to talk about. We did like this, we did like that. Oh! I remember now. But through the magic of television, that part will probably get cut out. One of the other big questions is, especially on roller claws, do we store the game pieces within the claw or externally in some sort of conveyor system or hopper system? And that's something, question kind of similar to like writ large for intake or claws in general. For this year, there may be a somewhat obvious answer of we're only holding 2 game pieces, so whatever fits, like just make the claw big enough to hold 2 game pieces, that's it. It's a lot harder to break the rules when your robot physically cannot store more than 2 game pieces.
Although that doesn't lend itself to the car wash robot.
Exactly. So something like this, but that has maybe a conveyor belt loop here and a further platform. Now we can intake game pieces and shuttle them through the robot and get them up towards our delivery system. So we're moving a little bit away from just gathering game pieces and more into like kind of that system-wide robot integration. But something like a car wash probably is not going to work well with a regular claw, because you have to get it from the claw into the next system.
Yeah.
So making sure that all the teams out there are thinking about how they link system to system to system and kind of really considering the full path of the game piece is really, really important at this early phase of the game. We're only a couple weeks in, but if you commit to a claw too early and you want to go with a pass-through, you're going to have to rebuild something, one or the other.
That's true. There are some teams who have decided to do split combination systems. So if you wanted to do an elevator delivery system up to score, but you wanted to do the 180 robot, there are some teams that would build in that dustpan into something like, kind of like a roller top claw that would grip it, go up to the right height, and then spit that out.
Yeah. These can, dual purposing mechanisms, that's a great way to save on weight, which is sort of one of our other big topics for tonight's show. Designing around weight. So anytime that you can double purpose mechanism, that saves you the weight of that whole other mechanism. So that's pulling weight out of the robot. One of the best advice that we have is weigh your robot early, weigh it often. As soon as you start to get some semblance of parts together, throw it on a scale, throw it on a bathroom scale. Doesn't have to be terribly accurate if you know that you're going to have a little bit of fudge room, and leave yourself maybe a pound or two for tournament inspection. And sort of figure out a weight budget. I think that's one of the other great
that's a good one.
piece of advice.
One other piece of advice to add: we are hanging both at the start and the end of this year's game, so where your center of gravity is in your robot is going to be another huge consideration.
Absolutely, absolutely. One of the data points or reference points that a team may be curious about, is your chassis. Kind of everybody's probably going to have one. Where do those kind of weigh in at? The tile runner, depending on which configuration, is about 11 to 13 pounds, all told. And so that's about a quarter of the total robot weight, and that's kind of a good number to sort of estimate around. So that means we've got a quarter of the robot weight to driving about. We're going to have some amount of robot weight for the electronics, the battery. A lot of those are fixed values. You know that you're going to have an expansion hub, a phone, a battery. So starting a table of all of those things will help you understand how much weight is left on the robot for all of your mechanisms and all of your special functions.
So there's going to have to be wires in your electronic system too, right? Danny, do you have a preferred method for estimating how much you're going to have on your robot?
Do it, weigh it, freak out that it's too heavy, and undo it? No, I don't.
I know that there are some teams out there who will actually weigh a spool of their preferred wire or any known length cables that they can't sort or make shorter. You also want to make sure you're accounting for your hardware as well. There are a lot of teams that'll forget. You got to weigh your rivets, you got to weigh your nuts and bolts and washers and all that stuff.
And I think weight consideration is something that a lot of FTC teams have considered in the past, but it's been like the weight of the arm or the weight of their end effector. They want to reduce the strain on their motor or their powertrain, and so you don't want a lot of weight out on the end of a long lever. But now we're just sort of taking that one step farther and considering it for the robot as a whole. And those other factors are still really important, but now we're just kind of adding one layer of complexity to the whole thing. And this year being a space game and sort of the critical aspects of weight and space and what that takes just seems to fit all the more about there's a very simple calculation in the rocket world that weight equals dollars. It is a specific number of dollars to get that pound of stuff into space. And so it is one of the single biggest considerations when trying to fly stuff to orbit is how much it weighs. So having weight on a space game, it fits.
Absolutely, Danny. As well as packaging, all that good stuff.
Absolutely. You mentioned earlier that we've been working on some prototypes. So I think maybe it's time that we do another sweet transition. We hide our big sheet of paper. We were working on a couple different prototypes. We've got some cool mechanisms here. So just off camera, I've got our sort of test and development robot that we saw last week. It's got all of its electronics on it, and I've been using it to demo and try some of our mechanisms. It's got a control system from last year, but still current. Phones, Rev expansion hub, and all that kind of good stuff. But one of the first things that we looked at was sort of just the simplicity of a claw. So this claw,
Ooh.
Oh, it blends into my shirt. So works like this. It's powered by a single servo off the backside here. This is our PicoBox Super Servo. The servo shaft and our secondary shaft here are geared together. They're geared 1-to-1. So maybe we can see some of the gearing in there. And so that means that we're using one servo to do all the work here. We can drive off the servo shaft here, and then these two just operate back and forth. And then one of the things that we did is utilizing some more of the S3 tube. We anchored in, these wheels don't spin, but we anchored them into the S3 tubing just to kind of be our squishy thing to kind of take up the space difference between the cube and the ball. And so they're also, so these are 35 diameter, super squishy, 2-inch compliant wheels. And
they're pretty durable, Danny.
yes. We've spun them to something north of
9,000 RPM?
9,000 RPM is just a little bit over 9,000 RPM. We have stretched them and pulled them until they fail. They will, I think, somewhere in the order of quadruple their length before they break and do crazy junk.
We have 3 levels of squishy for these guys?
We have 4? 3 or 4? We only have 3. We do only have 3. You're right.
Only for the 2-inch.
That's why I was
yeah.
mistaken. So we have the green, which is our super soft. The maroon, a little bit harder. These wheels are, the squishiness is measured with a unit called durometer. So it's more or less lives on a scale 0 to 100. The green is a 35, the maroon is a 45, and the blue is a 50. So that kind of gives a little bit of an example of how they stack up. On the 4-inch compliant wheel side, we do go into our black tread, which is
60.
60, exact, yep. And then we only carry it in the stealth wheel line. We don't have it in the compliant wheel, but the gray wheel is a 75.
And these come in different bores, don't they?
That is absolutely correct. So for all of our FTC fans out there, we have sort of the FTC standard 8mm bore configuration. Now we also have 2 bolt holes. They're on a 16mm bolt pattern, so they work with all of our nubs, all of the other stealth wheels, the hole pattern in the S3, our gears, our pulleys, our Ninja Star sprockets, and all of that kind of fun, cool, good stuff. If you're looking for something a little bit different, we have 3/8 hex and also 1/2-inch hex. So you can run those on Churro Light, do all manner of cool things there. One thing to keep in mind, though, if you're running on the hex ones, is because these wheels don't have a solid core to them, they're all squishy all the time, you can ratchet them around the hex shaft. So you won't get a perfect 1-to-1 rotation with your shaft when you put them like under load or something like that. If you get a game piece into your mechanism, your wheel may stop and the shaft may spin on the inside of the wheel. For a lot of mechanisms, that's okay, even preferred. Sometimes maybe not. Right. So for a drive wheel, definitely not.
Yeah, and determining whether or not your mechanism is going to do that is going to come down to a lot of prototyping. There is going to be a preferred speed for these wheels, and the amount of intake force that they're going against that is going to determine whether or not they're going to spin on that axle. So the 2-inch hex ones are a stretch fit over the axles, so they're actually a little bit undersized for what they're supposed to go into.
Yeah, so they'll be listed on the website as like a 3/8 hex or a 1/2-inch hex, but if you look at the print, they're actually quite a bit smaller than that because they are so squishy. All right, so I think maybe it's time for a demonstration.
Ooh, demonstrations.
All right. So I went through and I used the blocks programming language. I love it. It works for me. I'm a mechanical dude and I can program in blocks. So the tutorials in there are pretty good. It took a bit of time. I figured it out. But I have mapped this guy to open on A and close on Y. But we can go through and we can grab a ball and we can shake it all about. It's held in there really nice and strong. And when it's time to score, let it go. It'll do 2 blocks. If only a second block was within reach.
Can it do a ball and a block at the same time?
I have no idea. So we're going to do a live on camera first for the first time ever live demonstration. Back it up, yeah, right there. Nope, back it up. Whoops.
Almost.
Almost. So we're still developing. We're still prototyping a little bit. Maybe if the ball was in first.
Try that way. Almost.
Nope, didn't work. It's Close.
That's part of why you prototype, right, Danny?
Exactly. So we're playing around with this. We're getting a chance to kind of see what it's going to do. We started with the wheels in different configurations, moved them around, just kind of bolted and unbolted, added the fifth and sixth wheels, later to kind of fill in some of this gap. But maybe, like we were talking about earlier, maybe I only want to be able to grab one type of game piece at a time, so that way that makes my scoring a little bit simpler. So
that's a really easy filtering method, Danny.
I think we're going to call it a feature, not a bug. But yeah, so just nice and simple. We use some nubs, we use some S3 bits, all sorts of fun stuff going on here. But this one's a little pedestrian, a little mundane. Doesn't quite have the pop, zing, or pizzazz as some of these other mechanisms do. So we're going to put this one down, and now we're going to start to look at a second style of mechanism. And this is more of a roller claw. And so
that's got this C shape with the wheel on top, right?
Yes.
I like it.
And so we've got NeverS 3.7s here and here. And then they're mounted onto our PicoBox Leos. Here we've got a nice little divider. This is actually apart from the towel runner, repurposed for over here. And then we have some really thin polycarbonate. So a 30 thousandths of a thick sheet polycarbonate. This is really nice. It's really flexible. You can bend it. It'll hold a bend line. But you can also just cut it with the regular sort of heavy-duty kitchen scissors. So it's really easy to work with in that. On the output shaft of the motor here, we've got a compliant wheel. Now this is our maroon, so 45 durometer. So it's a bit stiffer than the green wheels that we were using previously.
But it's still got a bit of squish to it.
Yes. And then you see we have some funny bends, here, and we actually have two different styles. And so these look a little gnarly, but these are just kind of an example of our first generation prototype. So I actually did this one first. Had to put a few bends in it, thinking that maybe some different ways of holding the cube would work out a little bit better. It got further refined into this piece here with we took out some of the bends, and then we added some stiffeners, some more sheets sort of leafed in to sort of make the back bend stronger than sort of the floor bend.
Sort of like a leaf spring.
Exactly.
That's pretty cool.
That's exactly what a leaf spring is. And so the way that these work is we have two independent roller claws here, and so we can collect one or the other or both, but then we can also, so as one comes in and gets held in place, we can continue to fish around for the other, and we're not sort of doing a burnout with this motor here. We can turn it off. And then we can also hold and position these and let them go one at a time into their respective goals. So if we didn't grab two of the same thing, we have a bit more control, unlike the claw that we just saw, we have a bit more control about how we can dispense them one at a time.
That's pretty cool. So that could be something where you have the right trigger control the right side, and the left trigger control the left side.
Exactly. So we have some. We're still sort of working on maybe how much where the exact position of this is and where this goes in space. But once one of the tricks that Kevin learned while he was doing this is by cutting out a hole, we can get it to hold onto the cube pretty nicely. But because the ball is so much bigger, you can let it poke through the hole a little bit.
That just seats right in there.
And now you can use about the same amount of clamp force to hold in the cube and the ball.
Nice. That's efficient, Danny.
Yes. So Kevin was playing around with this a little bit earlier, and so he just kind of gave me the brief description of it. But this is just kind of a nice little mechanism, kind of thing that this would be out on the end of an arm, be able to go through and grab the different game pieces, and suck those in, and then carry them up and maybe do an over-the-top slam dunk into the cargo holds. So fairly nice, compact little mechanism. One of the considerations is it does have two motors way out on the end here, possibly on the end of a long arm or something. So
a lot of that will come down to the packaging. If you decide you want to go a little crazy and go with a right angle drive on that, if you can get some bevel gears out there, lots of different ways that you can package the gripping. That's pretty cool, Danny.
Absolutely. Yeah, so we can try to give this one a little bit of a go here, see if we can Usually this one just throws game pieces about more than it does much. It'll be cool.
So you're only plugging in one side right now, right?
Yes.
Okay.
So this is mapped to the D-pad on my game controller, so I don't quite have exact control over throttle, but I can control in and out. So it takes a little bit. We're still developing, but we're a couple weeks in, so we're still prototyping and developing. But we have we can intake the ball. We can get a pretty nice little grab on it, and then when we're ready to go up to the lander, we actually don't even need to get quite up to the lander because we do have a little bit of out that we can shoot the ball. Not quite launching, but we can give it a little bit of forward velocity so that it goes, or maybe a little bit more secure as we. About how we feel about throwing it into the goal.
That's pretty cool, and that's something that you can play with in the code. Make sure you're going different speeds when you might want to go slow when you collect, and much faster when you're going to be scoring those game pieces if you're using the same mechanism.
Yes, and so looking at how you might control something like this, playing around with those speeds. One of the things that we probably figure that we can do pretty effectively is map all of this to different functions on the joysticks. You do have a driver and an operator, so your operator could feather the throttle, but it's probably not something you need to do every match. You probably just need to figure out what the right set point is, and then you can map those to some buttons and drive in at a certain rate and drive out at a certain rate.
Absolutely. So, Danny, we do have two different kinds of wheels here, and we talk a lot about how squishy and compliant these wheels here. What if you don't want to have any give in your wheel and you want to use something like a stealth wheel? So it's still got that same grip you're looking for. What's a situation you would use that? I think this would work fairly well in that situation because you have so much give in that bottom plate. Can you think of some other systems where that might be a viable option for teams?
Yeah, definitely places where you have, maybe more of, instead of squish or whatever in the wheel, you have that, in a mechanical system, a pivot and a spring, something, to provide a little bit of traction down onto the wheel, but now onto the ball, but now you do need to roll sort of up and over to secure it in place. So you're going to want to make sure that you take care of that height gap, and that wheel does need to move up and down with respect to the floor plane. Now, depending on how you're maneuvering that ball into the robot, you may be able to just rely on the squish of the tiles to bring it in. But there's all manner of different ways that you could go about this. The cube sits at a perfect height, so if you have a hard wheel and the cube and there's no squish to anything, then you can sort of self-reject the balls and only bring the cubes into the robot. So again, if you have an intake optimized around cubes, then you may be looking for a solution like this as a way to sort of do your sorting before they ever get into the robot.
Absolutely. And these also do have a stiff center to them, so if you absolutely don't want to have to deal with any potential spinning, and you don't want to have to fine-tune the speed, or you want to go faster, then these are really going to allow for on a hex shaft. Stealth wheels are going to be a really great choice.
Absolutely, yeah. And one of the things that we don't have up on the table here is the 4-inch compliant wheel. So those use the same core, the same hard polycarbonate core as the 2-inch stealth wheel, except now they have an extra inch of compliant material. They look similar to our 2-inch ones. So those kind of give you the best of both worlds. But as you know, sort of in engineering and problem solving in general, there's no free lunch. So yes, they have the higher torque capacity. Yes, they're still compliant. They sort of mix both of those. But in order to get there, we now have to go out to a 4-inch diameter. So the packaging problem suffers a bit. And so that's just something to kind of keep in mind there. If you think you're getting the best of both worlds, you think you're getting both ends of a trade-off, you're probably paying for it some other place.
That's true. That'd really be something you have to consider in your packaging. Maybe you don't want a built-in belt to an internal conveyor system, and you just want that to loop up into something that'll flip up and deposit. So, that gives you your long continuous surface to a storage position if it's in an optimal shape for you.
Yeah, absolutely. And again, we don't need massive hoppers. We just need to hold 2 game pieces. But unlike robots that can hold, a ton of game pieces, you may not care if one of them bounces out as you drive. Here, we're holding 2 game pieces, so we really want to make sure that we have a good, strong hold on both of them, because if one of them bounces out, that's half of our scoring potential for that particular cycle. That could have a huge impact on what we're doing. So, a nice, fast collector, something that's easy to drive, easy to control, holds the game pieces really well. Those are going to be some of the highlights of things that you're looking for. And some of the other things, how are you going to, are you going to sort before it ever gets into the robot? Are you going to sort afterwards? We're going to have a lot more next week on sorting. My turn for the shameless plug. So keep an eye out for that. But yeah, so those are some of the highlight points to kind of keep in mind when you're designing your game piece acquisition system.
That's pretty cool, Danny. I like a lot of these options that you've come up with, and some of the ones that we just drew out on paper. It really gives you a wide array of choices, and you can tune all of them to your own team's personal style.
Absolutely. These work on so many different robot platforms, so many different things. They really can be tailored to however you conceive about doing it. So I think that brings today's episode to a close. Thank you so much for tuning in with us this week on Roundtable Ruckus. We hope you enjoyed our discussion about game piece acquisition, and we hope you learned a little bit about how we sort of deal with the weight constraints a little bit. We will be back next week talking about game piece delivery, and also a more in-depth discussion about sorting. And so that's going to be something that we hope you guys are excited for. So until next week, for the whole crew here at AndyMark, for Ruth, I'm Danny. We've enjoyed having everybody along for the ride with us. Thanks a lot and good luck this season.
See you next week.
Yeah.